Shall we start, sir? What is the status?
Yes, sir. Shall we start, sir? No problem, sir. Sir, Gurnath, sir.
Yeah, okay.
Yeah, shall we start, sir? Yes. So, heartily welcome third day faculty development program on conduct organized by EEE department, and welcome to our resource person Gurnath Gurrala Garu, and please hand it over to you, sir, and please accept our invitation, sir. Thank you, sir.
Okay.
Yes.
Okay, so I'm going to keep my video in off.
Yes, sir.
So that streaming will be good.
Yes.
Let me share my screen.
Yes.
So is it streaming on YouTube?
Yes, sir.
Okay. I'm not sure why this needs to be streamed on YouTube.
Because the Zoom participants are very limited, sir, so that we can plan like this, sir.
No, what is that?
In the Zoom platform, the participants are very limited, sir.
Okay.
So that we will plan like this, sir. We will directly connect it to that YouTube live, and then we will send a link to all the participants. They are clicking on that YouTube link and then directly get our lecture, sir.
Okay, but it will not be made public, right?
Yes, sir. It's not public, sir. We will after that we will automatically the link will be disabled, sir.
Okay.
Yes, sir.
Not sure where. Were you able to see my screen?
Yes, sir.
You can see my presentation?
No, sir.
It's not coming. One second. Okay, the screen.
Yes, sir. Now it is visible, sir. Sir, with your permission, once again, I will brief go through your profile, sir. So, because today participants are quite different from yesterday's.
Okay.
So that I'm requesting you, please give me the permission. Yes.
Sure.
Yeah. So, Dr. Gurnath Gurrala received BTech degree from SVH College of Engineering, Machilipatnam in 2001, and MTech from JNTU College of Engineering, Anantapur in 2003, and PhD from Indian Institute of Science, Bangalore, India in 2010. He was an assistant professor in SSN College of Engineering, Ongole in 2001 to 2, and Anil Nirkonda Institute of Technology and Sciences, ANITS, Visakhapatnam during 2003 to 5. He was a research engineer in GE Global Research Bangalore during 2010 to 12. He was a postdoctoral fellow at Texas A&M University, USA during 12 to 13, and also at Oak Ridge National Lab, USA during 14 to 15. He is currently an assistant professor at Department of Electrical Engineering, Indian Institute of Science. He received Professor DJ Badkas Medal for the best PhD thesis from Electrical Engineering Department, IISc Bangalore. He received IEEE PES Outstanding Engineer Award 2018 and INAE Young Engineer Award 2015. His papers received Best Paper Award in IEEE Engineers Meeting 2015, Best Poster Awards in IEEE Industrial Society Annual Meeting in 2015, and IEEE T&D Conference and Exposition of 2016. Two of his master students received POSOCO Power System Awards. And he is a senior member of IEEE and INAE Young Associates. His research interests include smart grids, power system stability, grid integration of renewables, microcontrollers, high performance computing applications to power systems, non-linear and adaptive control of power systems. Thank you, sir. Thank you very much. Thank you, sir. And please continue our session, sir. Thank you.
Thank you. Thank you very much for giving the introduction. Good afternoon, everyone. So I am Gurnath Gurrala from ISC, Electrical Engineering Department. First of all, many of you are faculty members. So I convey my traditional namaste to all of you. Today, whatever I'm here is because of the faculty members like you. So please bless me for all my future endeavors. So I will be going through a project which we have finished in 2019, which is funded by Robert Bosch Center as well as Robert Bosch R&D in Bangalore. So basically, the goal of this project uh, is to actually design hardware and software platforms for energy management in campus environment. Many a times the bulk powers is being consumed by campus environments, and we can actually optimize to reduce the energy costs. So in this way, I will go through what are all things we have done. There are so many things that are yet to be finished. This is supposed to be a bigger project, but it's ended with a small amount of funding. So let's start what we will be. So basically, campuses will have so many buildings, and they should be equipped with intelligent sensors. And there are a lot of devices will be there, like lightning, and then ACs, maybe pumps, there may be street lighting, charging stations in future, and there are a lot of equipment which will be using energy. So what we need to actually have is a framework where you can monitor all these energies and then take decisions on looking at where the energy is getting wasted, or what are the things that are happening in the grid within the campus, and then try to see what can be done through that. So one of the important thing is reasoned energy usage. What it means is um, basically you can understand the usage of the different components that are there in the grid, and then try to understand their behaviors and try to adopt your consumption to their behavior. So this is something, an important aspect that needs to be looked at. So I'll just give you what should constitute to build such a campus ecosystem. For example, if you take the figure on the left side, you will be having, let's say, only a building I'm talking about, but this has to be expanded for every building that you have. So you have a main board that is coming, and then this main board will actually go through the entire wiring, which will go to switchboard level. So at the end, everything that you are going to feed will be at the switchboard level. And there will be only 1 meter at the main switchboard for a building. But all these kind of houses, or maybe buildings, residential houses, or any labs, everything will be supplied through a MV transformer. So basically, you might be having couple of transformers in the campus. Now there is a need to actually start monitoring at every point of these. For example, we will be already having meters at these buildings. um, we may or may not have meters at transformer. I'm sure that we won't be having meters at transformer except for the incoming feeder to your campus, and mostly you may not have meters at some of the buildings also. But if you have, maybe those meters should provide you communication capabilities. But anything inside the house, absolutely no metering. So basically you need to actually develop technologies which are basically low cost enough and penetrate to every part of this and actually give you enough information about how much energy is being consumed. That is very, very important in future. So, and then you can actually do a lot of energy optimization decisions if you have control on the end devices. This is something which we will not be having control, because most of the switchboards are manual, and you may need to have some automatic things that needs to be enabled, which are today or very expensive. The next level that you need to do is data aggregation and analytics. So basically you need to collect data from all these points and then do an analytics on top of that to understand the consumption in the system. The other things are basically collaboration framework and assistive services. These two were not done in this project, but this can be done as a future thing. So what is collaboration? That means you have different sensings, you have different entities. Like not only energy, you may be having a water management system, you might be having a waste management system. So there are many things that may come into the purview of a campus. Now, all these things also need to be actually integrated into a single campus management platform, which essentially requires you to have a framework where you can exchange the data between the two different domains and understand their interrelationships and try to optimize the overall campus environment. Then you need to be able to provide some assistive services, which essentially give you personalized recommendations to different buildings, different users, so that you can optimize under different domains. This is something which is requires a lot of effort in software, machine learning algorithms, or any other intelligent algorithm schemes to be run on this. And I'm working towards that with my PhD students in the future. So through this project, what we have developed are actually two important things. One, we have developed a low-cost, open-source, hardware-based monitoring device, which samples at 32 kilohertz. We call it as micro PMU, which is nothing but a phasor measurement unit. A phasor measurement unit is something which essentially samples voltages and currents and then estimates the fundamental voltage and the fundamental current from the whatever measurements that you got. And it gets time-stamped with GPS. Because it time-stamped with GPS, you will get precise time-stamping across the area wherever you have. So that is something which we have built. In addition to that, we can actually do power quality monitoring. So the power quality monitoring essentially gives you flexibility in understanding what kind of loads that you have and what kind of power you are also sourcing to the customers, or you are getting disturbances from different switching events or anything that happens in the system. So all these are actually done on a small hardware, which is very low cost. So the cost of building this for us, just the hardware cost was about 69,000 rupees. And then we also built a smart switch. Basically, the reason we built this switch is that most of the times, if you buy a smart switch, doesn't have any flexibility for you to do any experimentation. They're all like closed things. So we want to have a research grade platform where we can do even some analytics on the switch itself. And also another feature that we want to give is the user should feel that whatever is, although there is a microcontroller behind the switchboard, the user should feel that it should be like a traditional switchboard. So the traditional switchboard, he should be able to go and switch on and switch off. And also he should be simultaneously able to turn on or turn off from his mobile or from a central location. So that is why we also actually built a smart switch. I'll show you what we have built. And then we also built an open visualization portal. So we took open source tools like Open-ADMS, which is developed by EPRI in US. And we have customized it and built it for, there is already a Linux version is available, but it is not working. So we made it workable on Ubuntu. And then we use that as a backend platform for analyzing the campus distribution network. And then we actually use GS mapping of all the substation locations. And we have used this for displaying the data from the hardware, and then even hosting the raw data so that people can actually do their work. After the data has come, they can actually do some algorithms and all that stuff. In addition to this, we also built some cyber security features on the developed devices which we have built. I'm not going to go through the details of this. And then we also built some advanced analytics both on the device as well as on the server. I will touch base a few of these algorithms if time permits. Right. So now I will talk about different kinds of hardware architectures we can think of. Let's say you wanted your campus to be made a smart campus, and you want to of campus automation, and it becomes a live test bed for yourself. Of course, you need to get a lot of permissions. Unfortunately, we don't have permissions inside our campus because of a lot of other critical equipment being there level to do a lot of stuff. So today, there is a lot of hardware architecture that is available. For example, microprocessor based, field programmable FPGA based, and then system on chip FPGAs. I will tell you what it is. It's nothing but a microprocessor or an ARM core and then an FPGA together. So these are different hardware that are available. When you choose a hardware, I caution you, don't choose a hardware which is open source. That is like hobbyist hardware. For example, things like Raspberry Pi, BeagleBone. These are industrial versions of those boards, which you can actually try to pick up instead of the hobby versions of those boards because of the cost. Because it will actually give your student a lot of experience in building on industrial boards. That is something that needs to be kept in mind. Okay, so we actually chosen a different hardware for this. So this is a hardware. This is built. This is imported from US. It is called as credit card sized supercomputer. So why it is called supercomputer? Because it has a lot of compute resources. It has an ARM processor and it has an FPGA board. And apart from that, it has a 16 core processor, which is basically, you can do some parallel processing on it. So basically, totally it has 18 cores because ARM has 2 cores and 16, so total 18 cores, and then you also have an FPGA on it. So we have chosen this architecture because the FPGA that is being used on it is Zinc. Zinc is an industrially proven hardware. So that's why we have chosen it, even though it is an open source hardware. At the same time, it also has a parallel processor so that students can be trained on how to do parallel programming. The problem with this particular board is if you buy this, you will only get this kind of a board. This is not amenable for actually connecting any external sensors for doing analog sensing, other kinds of stuff. So what we have done is we actually built a board. What you see on the right side, this is built by us, and this you can connect this board onto this board so that all the IOs, input output pins that are available on this board are now actually exposed so that you can connect maybe an analog front-end circuit, or you can connect maybe different kinds of sensors to it uh, through this board. So this is something which we have tried. And then what we have done, we also built an analog front end for a 415 volts, 3 voltages and 4 currents sensing at about 64 kilohertz sampling rate. I'll tell you why we have chosen 64 kilohertz. Because we want to sample at a very high rate, and then so that I can actually get a lot of surges. Because suddenly when your power is gone, and suddenly when UPS comes up or a generator comes up, there may be a surge on your system. There may be surge because of somewhere some short circuit happened, and then your equipment got damaged. Now, all these kind of surges are very, very high sampling frequencies required to detect such surges. So that's why we have actually chosen a high sampling rate. Of course, this sampling rate is also not sufficient for getting those surges, but we thought we can actually try to build some intelligent algorithms to detect this kind of surges, even with a sampling rate of maybe 32 to 64 kilohertz. So this is the hardware that we have used and built. You can see this is what the entire thing that is built by the students in IISc. So this is what I am telling you, this extra board that we have actually built. And for the parallel, you can see the parallel is here. This is only $150 is the cost of the parallel. And you can see the fan on it. And then you can see the front end board, which is actually used. And this is a Garmin GPS. And then we have connected the GPS to it. Now, I'll go through a little bit of details of what kind of developments that you may have to do on this kind of board to do, so that if when you are trying something, you will also keep this in mind. What is the goal of this particular hardware? We wanted to do a continuous waveform recording with high sampling rates. So we want to do the complete recording. And I'm telling you, if you want to have something which of this kind of hardware with a very high sampling rate and a continuous recording for a long duration, the cost of this hardware will be anywhere between 4 lakhs to 5 lakhs if you buy something commercial. Instead, you can actually do a low cost hardware. I'm sure after building this, and we can use this maybe within 1 lakh, we can actually produce this in a decent form for many universities to use this kind of a thing. So let me go to the next slide. So basically, the first thing that we have to understand, any hardware processing that you wanted to do. For example, I'm taking a case of a phasor measurement unit. So what you need to have? You need to have voltage and currents to be sensed. What are the first fundamental devices? You should have a CT and PT. Of course, that you cannot build. You have to buy the CT and PT as per the requirements of your system. You may want to do only 230 volts, or you may want to do a 415 volts. So you get the CT and PT. From the CT and PT, you will be getting maybe either it is reduced to 110 volts. Usually that is the range. The secondary of the CT will be either 110 volts or maybe 60 volts, depending on what kind of CTs you will. But industry practices in power engineering is to use 110 volts as the CT secondary. Of course, the low end low power CTs, they can directly give you either a 5 volts or a 10 volts based on what you want. And then that complete voltage has to be converted into digital. That is where the analog front end board has to actually be designed, which has to use a ADC, and then it has to sample all the data. And then you need to make sure that before it is sent to the ADC, it has anti-aliasing filter, so that you will be avoiding unnecessary aliasing in the system. The another thing that you need, it's very important nowadays, is to do a GPS synchronization. When you do a GPS synchronization, then there should be a method of actually making sure that your ADC is also synchronized. Okay, so that something is an important task that you need to build within your programming architecture on the hardware. And then PMU processing algorithm. This need not be a PMU. For example, you are looking at for relaying application, then you need to do a DFT and get the fundamental. And then after you get the fundamental, you may have to use a threshold based approach, or maybe you want to do a distance protection, so you can actually calculate the impedance and that kind of stuff, right? So then there may be a requirement that you need to give certain outputs. For example, these are the outputs I will be giving from my PMU: amplitude, phase, frequency, rate of change in frequency, and then absolute time. So you may have to actually use some protocol like serial to parallel interface protocol for combining your ADC output to a microprocessor. So these are all things that needs to be done. And you need to do a interfacing of GPS data also into the system. So I'll go through few small things in this so that you will understand much clearer. For example, I have to do for a current transformer. So I may have to have I may have a distribution transformer of this size, and then I may want to have a maximum current should be less than 1000 amps. And then I may choose a CT, which has only 5 amp. So 1000 to 5 amp CT. So depending on what I wanted to have. Now, what is the application of this? My application is mostly for measuring and not for protection purposes. So I am looking for a 0.2% accuracy CT, which you can select. But if say, no, I want to use it for protection purpose, then you can actually go for protection class CTs in your system. And then we wanted to actually design an interface from the CT to your ADC. The ADC actually takes voltage signals between 0.3 volts to 2.7 volts. So it cannot take whatever the voltage. So you have to drop the voltage of whatever current that flows through has to go through a potential divider circuit, and then you have to make sure that the voltage is dropped. The voltage across this doesn't exceed this voltage limit, and then you can actually calculate based on that. You can do some burden calculations. You can get these details on any standard analog front-end design papers where you can actually provide these design details. So something that you need to focus on this design where the analog front-end essentially needs to be built. For example, whatever I'm showing here is what is realized in this particular board. So this is this board. So what I am showing as a circuit there, that is what is shown here as a board, right? So you can see the similarity of what you are seeing there. I'm sorry, I have a problem in the presentation. Just one second. Okay. So the next step that you need to actually do is you need to look at what are all the interfaces that you may need. For example, for me, this Jink board or this particular paralleler has voltages maybe around it has a 3.3 volts as the input, but all my external peripherals require 5 volts. So I have to use level converters, right? So you need to make sure that there are level converters which are used so that you can actually adequately connect to the devices that you want. For example, you want to connect some temperature sensors, you want to connect some humidity temperature or any other things. You may want to connect some electronic rain gauge and maybe a wind direction that you want to find out. So all these sensors, if you need to understand what that sensor voltage is and how I'm going to connect. So these things that needs to be taken care while designing this hardware. And what kind of protocols you wanted to use. You want to use a serial interface, you want to use a UART, or you want to use RS-232. All that stuff needs to be decided, and you have to enable all those things on it if you are using a custom board. But most of the time the custom board, for example, parallel doesn't have such a board, so we had to develop all these things by ourselves. And then you need to look at how you are going to manage the resources on the board that you have. So on our board, what we have a FPGA, we have an ARM core, and we also have a 16-core processor. Now, the way we have to work on, we have to see what needs to be done on, say, FPGA. FPGA something is very fast, and it can actually, it's like any fast processing things that you want to do. It can have very high sampling and all that stuff. So it is good for doing real-time operations and continuous operations with data intensive, compute intensive tasks. So what we decided that we will use FPGA for data acquisition at a very high sampling rate. So we wanted to do it at 64 kilohertz. So we have designed the complete FPGA inside so that we will have data accessed at about 64 kilohertz. Right now, we are using this only for 32 kilohertz. And then what we need to do is, okay, this data is accessed in the FPGA now. How are you going to send this data to the network, right? To a server where you can do some analysis on it, or you wanted to do extra analysis, then FPGA is not a good thing for you to actually do a continuous this thing unless you are an expert. You can create software processor in FPGA and do a lot of things. But I'm just saying that just to do a regular task like you do it on a microprocessor or a microcontroller on an ARM processor, doing it on FPGA is bit of experience needed. So better you do such tasks on, let's say, ARM core, because it has 2 cores and you have a full-fledged Linux running on it. So you can do a lot of work on that. So we decided to do what is called as compression of the data, because I'm actually getting 64 kilohertz data. I need to compress and then only I can send it to the server. So if I don't compress, then your bandwidth will be completely used. And so that is not a good thing. So that is something we have decided that, okay, we will run all the compression algorithms on the ARM processor, and also all the codes that needs to communicate to the server, we wanted to run on the ARM processor. And the next thing that we need to actually do it, we also have to send the data secured, right? So we have to run maybe encryption algorithms and then storage related algorithms. Why? It means that I want to store in a particular fashion, then I need to make my data to be encoded into that format and then has to be sent to the server. So all those things are actually taken care on my ARM core. Then we wanted to do power quality analysis, which requires a lot of data to be saved and used. So then we decided, okay, there is a 16 core processor is available. We will try to use that processor and do the complete power quality analysis on that. So what we did is basically the PMU is basically developed completely on FPGA. You can see on the top. And then and complete data processing of 64 kilohertz data is on the FPGA. And then we have done some things on the ARM core processor. This processing system is ARM core, and I will show you about the parallel processor later. Okay, so that's what we have done. So there is a small technical details I wanted to actually tell you. Data has to be acquired from the ADC. So it needs a particular process. Now, the process that we want to follow is that whenever there is a trigger, then only you should start the ADC sampling. Now, how to set this trigger? Usually this trigger is set by one internal clock, which is generated and it keeps on going it. Now there is a requirement for us that we have to sync this to a GPS timestamp. Now, what do you mean by GPS timestamp? If you take any regular GPS, and these GPS will have what is called as pulse per second. It's a signal that is generated by the satellites, and that signal will be given to us through this GPS. And this essentially synchronizes to a microseconds error, less than microsecond error. So that means you are getting a very precise timing using a GPS. So this pulse per second means only at every 1 second you will get this pulse, which gives you time information, it gives you location information, and it gives you so many other things. So what you need to do is this pulse, it's just a pulse. It's like a pulse train you will get at every 1 second. So you have to basically make sure that your ADC is synchronized to this particular pulse. So that is something which we will be doing in this particular driver. So this is a specific driver that needs to be written either on your ARM core or on your FPGA. So we used FPGA, so we have done this on the FPGA. So basically, this states there is a reset signal which done, and when the reset is 0, it gives a clock, and there are some internal commands. Basically, it starts start signal. Okay, then the moment the start signal is given, the ADC is configured for data acquisition mode, where you need to actually look at your ADC data sheet and understand how to do this, and which signal, which pin needs to be made high and which pin needs to be 0. So all that stuff. And then you can see that here, wait for data ready. So the ADC, as soon as data acquisition mode is enabled, until the data is completely acquired for that, from all the 8 channels that you have, this data ready signal will be 0. Once everything is acquired, immediately data ready will become 1, and all the data will be now ready. So one see data flag 1, immediately internally you can actually just take the data and send it to whatever you want. So this is a kind of flow chart, I would say, state transition diagram that you can use to design your driver. And similarly, getting from time from GPS device. So this is also very important, and you need to go to the GPS datasheet and understand how it works. So you have to first set your baud rate for the GPS depending on what GPS you're using. Here we are using Garmin GPS 18XCV, which is the model, and that needs a 38,400 baud rate. And then we have to restrict the output sequence. This actually sends this particular string GPRMC. So this is basically there are different data sequences that are being provided by the GPS. You have to understand what kinds of data sequences, and the data sequence that we need is this GPRMC. These are the things that we need to know. So geographical locations, pulse, and then there are other things the name of this indicates. So basically you need to restrict only to that data. That means the whole data that is sending, you need to select only the required things from that, and acquire data and time information using UART protocol, because here the universal protocol, this is UART, is being used for, because this GPS actually supports only that particular thing. So how do we do this? So this is, again, I have actually shown you one GPS device. How the flow, the state transition looks like. Again, there are similar things. But one important thing is that there is the RX receive and transmission signals will be there, and you have to actually detect the edge of that. Then the data ready will be set to 0. And after that, you need to look for the data. In the data, there is a dollar signal should be there. And from that, if that is received, then you have to, that means out of the data, from dollar, you have the required data. So you find out how many bytes you need to actually collect, and then immediately take those many bytes. And then once all the things are actually extracted, you can say data ready equal to 1. So this is actually specific to a given GPS, but more or less the steps will be more similar. So this is something needs to be developed. And then of course, whenever you are actually sending signals to FPGA, to different drivers, because I'm writing a ADC driver, I'm writing a GPS driver to actually get the data from these two devices. There will be some problems, what is called a signal bouncing problem. This you might have heard already. So instead of an expected state like this for a given signal, there may be some bouncing issues. So this can be taken care by using a debouncing circuit like this. These are standard debouncing circuits which avoid this transition in the middle. And we just simply pass all the signals from any external device, for example, GPS, sensor, anything that you actually connect to this particular compute module, we pass through a debouncer so that we have a safe transition detection. So this is something that needs to be taken care in designing your front end and then data dragging inside. This is one example of what we have done inside my lab. So you are all welcome to come to ISC anytime you happens to come to ISC Bangalore. So you can drop an email. So this is something, just the incoming of my lab. I have passed through CTs. You can see these are 4 CTs. And there are PTs. So the bottom are actually the PTs. Of course, this wiring seems a little bit horrible because this is done by students. But nevertheless, this is done with proper security so that whenever something happens, uh, this CB, whatever, will get tripped. MCCB will be tripped. So this is the overall setup that you can see what we have in this at EE lab. Of course, this particular board, what I have shown earlier, requires some power supply. So I'm giving a separate power supply, and I'm using UPS to power this, because even if something happens to the main power that I'm getting, this device should function. So that's why I'm using UPS to actually connect it. So this has been deployed for more than 3 years now, and it's working perfect. It's an open source thing that we have developed. So that's all about the first part, which is the hardware that we built. The second thing is basically a smart switch. So this is the size of the switch that we have built. The advantage of this, what we have built, is it has only a single relay. It has a Wi-Fi on board, and it has only very few components on it, like only 3 or 4 small transistors. That's all. So it's not too much of part count. So because of that, you can actually use this very safely. One feature of this is, for example, suddenly on the onboard Wi-Fi, which is a microcontroller, if it gets burnt or something happens to it, still you will be able to use your switchboard like your manual switchboard. So most of the switches that today are available, if the onboard manual is gone, I mean the Wi-Fi board is gone, you cannot even use your switch. That is one thing. Another thing is some boards now are slowly coming where you can do simultaneous manual and Wi-Fi, but when we started this work, something is not available, right? So this is the overall block diagram. So we have this small version doesn't have the sensing, but it has everything that you need. And the other one we have is a second version with sensing we have built for 4 relays. So you can actually take one switchboard with 4 sockets, and you can use this. You can control with your mobile all your things, and also you get voltage and current. So you can actually see how much power you are actually consuming. So this is the next version that we have built, which essentially has a lot of things, and we are trying to do a commercialization of this. We started, of course, there's a lot of software is being built on top of this through a company called Urja Links. I'm one of the co-founder. I will tell you some details later. So basically, any dumb device that you have, you need not spend a lot of money for making it smart. And this switch for 4 sockets would cost you something around 2,300 to 2,400 rupees. And a 15 amp one cost you around maybe 15 to 2,000 rupees. So that's the maximum cost that you can have on this. So as a whole, I'm actually trying to tell you what are the overall things that should be there in a campus management system. Of course, this is done on a platform of open source, but you can do it on any platform. So a front end, and of course I'm using FPGA, so FPGA specific drivers need to be done for doing communication with the remaining things what you want to use. So for example, the FPGA communicates the data using the SPI protocol with the 16 samples buffer, and then it sends to different applications. For example, I have an application where I'm going to compress all the data and send it to a server. On the right hand side is the server. I have an application which is PMU. I have another application which is power quality analysis. There are other applications which I'm not going to discuss. It takes a lot of time, where we are using this for edge computing in smart grid. For example, if you develop a relay, and relay can even do a state estimation on top of it if it can acquire data from other surrounding relays. So these are the things that can be actually explored as edge computing research. Okay, so what we have built, basically a software to even support the hardware. So the software should have, this is the generic software framework. The software should have database layer. So basically all your sensors will have to send the data into this particular thing. So, and this should have history. You should have some data that is historically saved data. There should be some data which is basically predominantly static data and predominantly dynamic data. For example, what is static data? Okay, I have so many switchboards in your system. Yes, that is static data. But so out of those switchboards, some switchboards are on, some switches are off, some transformers are on, some circuit breakers are off. These are all dynamic data. So you should be able to easily use the dynamic as well as static models in your data framework. And then from the database, it should be able to send to a cloud. Basically, this cloud can actually have different applications running. In our case, we are using power quality analyzer is the only application. And of course, we are doing a geographical mapping of all the transformers in your system. And then we have this data acquisition layer, which actually sends the data to the data layer, as well as it sends to the application layer. So this data acquisition I have already discussed with you. One part we have discussed is the smart switch, and the other part we have discussed as the PMU and power quality analyzer. You may have other things like circuit breaker statuses. You may have environmental sensors. For example, the smart switch can have maybe temperature sensor. It can have humidity sensor and all those things. It can have some infrared camera to see how many people are there in the house, and so many things that you can actually do. Right, so this kind of an architecture is what we have actually used, and we used what is called as common information model. This is a specific IEC framework for having the data to be stored in control centers. So we use a common information model so that tomorrow, if your campus network has to be shared with a distribution management system for them to actually do some scenario creation and all that stuff, it is better that it is in a common information model. So we tried something on that. So this is how the visualization actually looks like. So we call this as Open-ADMS. This is built by a student of a student. And what I'm showing it here, a couple of transformer locations. And these are nothing but substations within IISc campus. And each substation, you can see the numbers it shows. The numbers actually shows the number of transformers that are actually available. Something black, it shows that this is not an active transformer, but green means it is an active transformer. And then there is some blue boundary that is, okay, so we are also using the devices for doing some system level tasks. So this particular transformer is where we have installed some sensors which do system level tasks. So like that, we can actually have a lot of things on this displayed. And then you can actually click on schematics. I'm not showing here, but click on schematics. It will show you the electrical single line diagram of your campus. So you can actually add that to your thing. And then since OpenDSS is already at the background of this, you go to static analysis and click and say, run load flow analysis. It will run the load flow analysis of your entire campus, and it will show you all the voltages at different nodes. You can also do other analysis. We have not enabled those features, but this is something which can be actually added by yourself since the framework is already there. And then dynamic data is essentially, you click the dynamic data, then you can actually onboard all your sensors like switches. You can actually onboard all your IEDs or your PMU devices, and their data will be displayed as continuous bar charts, so you can actually see the data. I don't have any pictures. Maybe I can try to see if something I have. Of course, if you have some solar data from some third-party vendors, you can even import that solar data. We did that because we have one solar installation, and we tried to actually import that data into this system. So like this, basically, you can actually have a lot of things analyzed in a single web portal. Remember, there's a lot of development effort, and students will get a lot of expertise in building things. This is something today India is actually lacking. We only train our students to read and take books and ready and finish the exams. That's all we'll teach them. All our engineers are not taught on doing things. This is something very, very important. So this is you can actually encourage your students actually. And frankly speaking, I'm telling you, I'm not an expert in hardware, neither in software. What I have is the intuition and ability to do or guide the students so that they can actually accomplish the task that we want. This is something as a teacher you should gain that experience. You have to read more. You may not have the experience of actually coding yourself and all that stuff, but you have to gain enough knowledge so that you can guide your student. So that is something a very important thing. So this is something a middleware pipe, or what I would say is the data pipe from your sensors to control how it is happening. So for example, parallel board, it uses what is called as publish and subscribe mechanism using MQTT protocol. This is the recent, this is the latest things that you are seeing for the last 4 or 5 years. So all the data will be sent. These are all encoded in a particular format, and then they are sent to a server. This server, everything is actually designed by, developed, the backend is developed by the project team, and they use what is called as Corinthian middleware with RabbitMQ as the backend, PostgreSQL. These are all some software tools that are open source available to build all these things into your system. So similarly, we have used the middleware pipe and then data pipe basically. So there are different types of data pipes. What data? I have a fault recording data, I have power quality data, I have PMU data. Now all these three data has to be sent parallelly, almost parallelly on the network in a way that the network doesn't get overloaded. So there are different ways that this data has to be done, and they need to be saved at different time scales, because PMU data comes at a maybe 100 samples per second, whereas the fault recording data comes at 32 kilohertz. Now, both have to be saved, but in a different data format. So the time scales are different. So these things need to be looked at. And then the next thing that you need to do is you should be able to query. That means question your database. Hey, I want to see this particular data. So the database has to have the ability to do very good querying, and then you can use that for displaying the data. So basically, you can query the data and display the data, which requires, again, a framework for students to actually establish. Right. So that's what about the complete development. Maybe I will pause a little bit here and ask any questions. Are there any questions from the audience? Am I clear so far what I have discussed? Yes. Hello.
As participants, you have any queries, please ask it immediately.
Yeah, am I clear? Is it audible to everyone? There is no issue, right?
Yes, sir. No issues, sir.
Okay. Any questions so far? So that means nobody understood anything. Okay. Hope you will get some information. Yeah, if there are no questions, I will continue.
Yes,
Hello?
Yeah,
yes, sir.
ask it.
Yes, sir.
Any questions? Hello?
Many questions from the audience.
Carry on, sir. No problem.
Okay, so let me continue then. So I will now talk about the applications that we have built. Whatever I have told you is the things that needs to be built as the minimal infrastructure that you need to build. And you can actually ask your students to do all this stuff. And I'm telling you, they will be excited in building and they will learn a lot of things from this. Okay, so we have actually done a couple of things as applications on these devices. For example, on the ARM core, what we have built is a compression algorithm. This compression algorithm is an advanced algorithm where just by looking at the samples, it will tell whether there is some kind of a fault data is there, or is it something like a regular beautiful sinusoidal wave, or it has some harmonic content and that kind of stuff. So this is something which we are still work under progress. So basically, I'm not going into this too many details of it. So basically, the requirement here is I need to compress the data because I'm sampling at a very high rate. So what we will do, we do take the sampling and then store it, buffer some data, and then pack it into a small string, and then we will actually that what is the procedure we are using. I'm not going to the details. You can go to the papers. So once we pack it as a string and then do some processing on that, what is called as differences. So basically, we take a difference between different samples within those 16 samples, what we show in this FYFO. And then we look at, okay, how many bits are needed to save this particular data. Depending on the number of bits that I need, I would say if I need more bits, that means the data is having so many high frequency components. If I need only few number of bits, then I can say that, okay, the data doesn't require so much of space. So now I will send a very small packet. So something like that we will do compression. So the way this happens is, if I see some kind of a fault data, it will send the data as it is. If there is some kind of a fault, then I cannot actually compress more. Or if there is no fault, I can send the data with just maybe what is the peak voltage and what is the frequency. That's all. Two are enough for me to construct the waveform. So like that, we will do some things in it and perform the storing. So that is something about the this particular framework. So what I'm saying is, this particularly we'll do packing of all the bits and then send the compressed stream to the thing to the server. So we did some experiments and we found that we received very nice compression ratios in the system. The TL is basically a parameter that we use in this algorithm to achieve based on what kind of data that we actually see. Okay, so for example, I have this kind of data which is simulated. It has a small glitch here, right? So now if you see, the remaining portion is very nice, so I don't need to compress much. And this portion I need to take uh, as it is. So you can see that this portion requires more bits. The top portion requires more bits. At the bottom portion, I don't see any of the things. So it can be with very low number of bits. I can save the entire data. So this is something that you can actually understand how your algorithm is working using this particular approach. So then we also implemented some phasor measurement algorithms. So there are very standard phasor measurement algorithms that you can take. But one of my students has worked on two kinds of phasor measurement algorithms using phase locked loop mechanisms. And the other one is using what is called as Steger energy operator. So what we built is, everything is built on FPGA. So there's a lot of work involved in when you do it in FPGA. So you need to have all these things in it. So you need to have a GPS driver, ADC driver, which I have already discussed, PMU controller and PMU algorithm. So basically these two are nothing but you enable PMU action. That's a simple controller, but algorithm is the most important thing. And then in FPGA, since the data rate is very high, I have to use what is called as AXI interconnect, which can facilitate a lot of high data rate handling within the FPGA. So that is what something we have to use all the drivers for. Okay, so we did some comparison of different types of PLLs with respect to the standard called IEEE C37.118. So there are so many tests that you need to do, and we checked different PLLs we have implemented. So basic PLL also implemented and defect PLL implemented, but on the hardware, we only implemented defect, but in software, we implemented different things, verified and said, okay, so you can see that some PLLs doesn't meet some of the requirements of the standard. All green are basically the ones which meet the standards. So you can see that, for example, defect PLL and Park PLL, there are different types of PLLs. they actually pass a lot of steps for the rate of change of frequency, whereas frequency estimation, they actually fail in a couple of tests. So like that, you can actually do an analysis. And once we picked up defect PLL for implementation on the hardware. So I'm not going to the details of the hardware. It is actually very significant effort, but student actually got placed in Intel because of his effort in the hardware. So basically, he tried to actually implement everything, and then you can see that some resources are actually going very high. So he has to actually do a lot of effort in reducing the resource utilization. What is resource? On the FPGA, you have only so much of computational modules. For example, flip-flops. These are RAM and other what is called lookup tables and all those things. So these, you cannot actually go to like 100% usage of it or beyond 100%. So you need to reduce them. So except for IO, this IO is something which is, if you use all the IOs, then this will exceed, but we won't be using all the IOs. Because of that, this is okay. But remaining things are actually green. That means less than 50% you can actually get. But you need to do a lot of optimization. This is where students' expertise will be very much important. These are some kind of results. You can see we have estimated the frequency from the lab, and this is perfectly following with two different algorithms. And then you can see that this is on the right hand side, the voltage measured, the accurate voltage that is being measured using these algorithms on the hardware directly. Then the next thing what we did a power quality algorithms. What is power quality algorithms? You need to find out what are the harmonic content in the system, what is unbalance, how much unbalance is present in the system. There are so many things. So this itself is a very costly. If somebody wants to buy a power quality analyzer, it will be at least 2 lakhs to 3 lakhs is the cost that you will see. For laboratory grade and for research purposes, which has continuous monitoring available. Okay, so what we did is we have implemented this on Parallella. So we looked at a standard. This is the standards for IEC standard for different things. So we have to calculate all these things. You need to calculate RMS voltage, active power, crest factor, total harmonic distortion. And you have to do that for peak value, RMS value, many things. So all these things needs to be calculated. So again, you have to find out up to 40th harmonic. That means minimum 2 kilohertz is the frequency that needs to be done. And you have to take at least 1024 point FFT. So 1024 points have to be saved to perform the entire FFT. So computationally on a small device like Parallella, it is big challenging. So this is something which we have tried on the Parallella. Apart from that, we also tried Flickr implementation. Flickr is something which will tell you whether you have, if Flickr is not in proper bounds, then you will see that your eye gets irritated when you see a light. So this is something which needs to be avoided as per the standards. And the Flickr implementation has a particular architecture which you need to implement. So this is the architecture. Anybody can look at this particular thing, and you have to implement all these blocks inside. So we have implemented these in the system. So what it has to do, it has to detect sags, it has to detect swells, it has to detect interruptions. So we have to have all these parameters to be measured, and we should have long duration as well as short duration events to be detected. So we have different choices for actually implementing FFT on the parallel processor. We have a binary exchange, we have a 2D transpose methods. So what we have looked at is, you can actually go through this particular book, nice book, talks about parallel computing, and many students can actually go through the algorithms and then they can try on this particular hardware, or also on your regular desktop computers, which today have 8 core processors, 16 core processors. for parallel computing. So finally, we have decided to implement binary exchange compared to the 2D transpose method. Okay, so and choice of development environment, because the parallel is a specific thing. They have provided different environment, so you can use any of the environment, but we use the last one, Epiphany SDK, because this is something which allows you to lot of customization done. The others have a lot of difficulties, so we use this to program. This is programming is the main. So how we have done, so basically this is the overall implementation, how we have calculated. So we get 32 kilohertz data, and then we pass this, because I don't need 32 kilohertz for power quality measurements to be done, because I only need up to 40th harmonic. So 2 kilohertz. So at least double that I need the sampling frequency. So I need only 6.4 kilohertz. So I take the 6.4 kilohertz, and then we will basically buffer it and then send it to the binary exchange platform, and then actually get the indices of PQ indices at different intervals. So basically, if I'm sampling at 64 kilohertz, doesn't mean that I'm giving all the output at 54 kilohertz. The output comes at 5 hertz. So that's the meaning of that. So so in the cycle, so 5 hertz cycles is what 5 hertz is what we will be getting. So that means 1 by 5 is basically the 0.2 every 0.2 seconds, like that we will be getting the data out from it. Similarly, the other thing is actually sag and swell monitoring, but this requires a complete 66.4 kilohertz. So we take that, and then we have other modules like Flickr, which is developed, and it gives you different parameters. So this has to be mapped to the 16 cores that are available. So we have mapped to different processors. For example, one processor does harmonics, couple of processors does Flickr, couple of processors does V&I indices calculation, couple of processors does sag and swell. Like that, FFT is actually fundamental for all of these. So we use all these processors for FFD. So this kind of thing has been developed by the students, and that's all on the implementation on the device. So then we have some artificial intelligence techniques. There is no bound for this once you have the data. But one important thing that I wanted to tell you guys is, for any artificial intelligence techniques to be used, you need to generate enough data. And for generating enough data from experimental situations is not going to be useful. The reason is you may not have so many events being captured in your physical system. So for that, you need to actually simulate a lot of such cases. Now, if you take some commercial software like EMTP, which is an electromagnetic transient program, where you will be able to simulate all kinds of transients and data and all that stuff. How much of data you need to develop? At least you need to develop like 2,000 to 4,000 cases. If somebody has experience in actually using EMTP-RV and wants to do 2,000 to 300 cases, I'm telling you, it takes like hell just to actually turn on, turn off, okay, fault at this point, fault at another point, fault for 5 milliseconds duration or 20 milliseconds duration, 5 cycles durations, fault with different resistance components, fault of single line to ground fault, double line to ground fault, so many things that you need to actually create. On top of that, you need to create harmonic events. Now, if you want to do that automatically, some framework has to be available to you. So what we did is actually something similar to this, using a commercial package. We used MATLAB to run the EMTP-RV automatically so that you can create hundreds of cases. Just click and leave. And after 1 day or 2 days, all your cases will be simulated and you will have the data stored. So the framework is what I wanted to actually explain how we are going to do this. One good thing with all these circuit platforms is that they have what is called as net list file. What is a net list file? This file essentially tells you how the components in your simulator or in your network are connected to each other. That is what this netlist file tells. So what this internal software does, takes this connectivity information and then builds corresponding differential equations, and then it solves. It doesn't need a GUI, just netlist file is enough. Now, if you want to do different cases, simply go to that netlist file, change the netlist file, and give that as input to your commercial package. That is what is required. So what we did here is we looked at the EMTP RV's netlist file and how different components are created. And then we wanted to change a fault. We can do this using this. Okay, so the overall fault scenario generation I can explain. For example, what are the things I need to do? I need to change the fault location. Fault location can be at a bus or it can be at a branch. And when I do a branch fault, I should maybe do a fault at 10%, 30%, 40%, 50%. Anywhere I may need to do this fault. Or on a bus pass, if I want to do, I may have to do only a type. What are the types? LG, double LG, triple LG, ungrounded faults. Similarly, in the branch also, I may have to do all these faults. After the faults, there is another thing that is very important. What is important is incipient time. The fault is happening at which point? Is it close to the 90 degrees of the voltage waveform, or is it close to the zero crossing of the voltage waveform? It has a lot of things on it. And then you need to do even fault removal. Should I remove after 4 cycles or 2 cycles? Shall I do a very short duration fault or a longer duration fault? All these things are actually becomes a different scenarios. And after that, you need to have fault resistance. Fault resistance depends on, tells you whether I'm having a high impedance fault or I'm having a low impedance fault. Depending on the type of fault, the resistance value may change from anywhere from very small value, that is 0, to a very high value, that is hundreds of ohms. So all these have to be, if you just look at, this is a permutations and combinations. Just for a 5 machine system, if you take, you will see that it will generate so many cases. So doing that kind of thing is automatically something which we have tried. So what we have tried is, first we created a block called fault block. This block has different resistances, and this has one point. This point is where luckily in a netlist file, what you need to do, if I say that this bus is basically bus number 5, if I just say this as bus number 5, then this block will be connected to your 5-bus system, bus number 5 automatically. So that is the advantage of this netlist file. So just you need to change the bus number to connect it at a different bus. For example, I put it here, bus 1A, 1B, 1C. That means A phase, B phase, C phase, all 3 phases should be there because this is a 3-phase network. So now if I change this bus 1 to bus 2, so what you need to do, take the netlist file, search for this particular name fault block. Then you will go to that particular code. And at that point, you just need to simply write bus 1 instead of bus 1, you write it bus 2. Then it will automatically create a fault at bus 2. And then you can see a lot of other things. Resistance value of AB, AG, BC, BG, CA, CG. Initially, I'll keep these values at very high value. And then these like 1000 M means 1000 mega ohms, I actually put it. And this can be changed automatically. Now I make this to be 0.02, then it's a short circuit. 1000 mega ohms means it's a fully open circuit. So automatically this netlist, I know how it gets created, and this netlist file only I will change to create a different fault. Something like this can be done. And how do you actually use this netlist? Actually, most of the softwares allow you to run your software from command prompt. You can even call your MATLAB from command prompt as matlab.exe. If you type, MATLAB will open in your from your command prompt, MATLAB will open. Similarly, many softwares allow you to start from command prompt if it is Windows. Even in Linux also, you can actually invoke from command prompt. So the good thing is, for command prompt, when you are invoking, simply give the name of this particular run without even starting your hello.
Yes, tell me, sir.
Somebody has muted, something is saying, okay.
Okay, okay, sir.
Okay, so for example, I have created this kind of a system and its netlist file is available to me. First time you have to create the system. I'm also doing an automatic way of developing any system netlist file, but it takes time. So we need to create a lot of faults, so you can do using this. Okay, so this is an example. I'm just saying that now the sky is the limit for you. Any component, let's say values that you need to actually change, for example, transformer, the name of that will be available, something like this. You need to search for that particular name. And then you have to understand where the value of the transformer is there. Is it a 10 kVA? Resistance is 0.1 ohms or whatever per unit it may be. So you need to understand where that value lies. For example, 1000, I know that this is the value of my resistance. So I only need to check for this particular value and replace it. So something like that we can actually create. So I think that's all I have on this. Of course, using this approach, I have actually, one of the student has done a neural networks based fault classification algorithm. So you see how many types are created. For example, fault distance, 15, 30, and 45. This is in percentage. Fault inception angles, 0 degrees to 330 degrees, because the entire cycle I need to cover from positive to 180 degrees to 360 degrees. Fault impedance, you can see the fault impedances are different. Fault duration, I'm going to do 6 cycles faults, or from 1 cycle to 6 cycles faults. Fault types, AG, BG, anything. You can see that for all these, I will be getting this kind of waveforms. Now all these waveforms, I need to create automatically. A big database I need to create for my machine learning algorithm to run. 10, 15 waveforms doesn't work. Even 1000 for that matter doesn't work for your machine learning waveform, machine learning. You need to create like thousands, 20,000, maybe at least 3 to 4,000 cases needs to be developed. So this is where this kind of techniques will work. For example, I've done this. This is a small project by a project staff. So you can see that the machine learning algorithm he uses actually has a lot of accuracy, but this took a lot of time for him to actually get the accuracy level. And then the time that is taken for him is this much time to detect whether it is faulty or non-faulty, using different kinds of neural networks and all. Anyway, the other thing that we have done is also a machine learning algorithm called symbolic dynamic analysis, which essentially changes your data of 1, 2, 3 numbers into symbols. And then from there, it does some kind of analysis. I'm not going into the details of this. So these symbols patterns, how many times a particular pattern in these symbols are actually repeated, and that will be actually shown as a histogram. It's a probability histogram. There is methods of converting this. And then from that, you can actually say whether there is some event happened in the data or not. So I will show one example only. So for doing this, you need to take the input signal, transform it to some domain. We are using wavelet here. You can use different kinds of algorithms here, and you need to do some symbolic generation. Then there are some specific methods, so that I even don't have a very full detailed knowledge of this. This is something done by one of my postdoctoral student. So what you do is basically a partition of the data into different clusters, and then actually see how many times this particular cluster is going to repeat, and then calculate the probability of that particular cluster. Essentially, that is the meaning of this particular thing. And then you will be, depending on the probability, you can actually calculate what is called as anomaly measure. That means if you take a clean waveform and you calculate the probabilities, that is your reference. And then you take a waveform which is corrupted and then compare the probabilities with respect to the clean waveform and say, hey, there is an anomaly. So that is something is what is used. So this is the flowchart of what I have explained. This can be used for many things. So we have used even for fault analysis. We also used for power quality analysis. So both we have used. For fault analysis, we have also used, in addition to this, if it detects fault, then it also actually tells me a classification. So this is something we have tried. Okay, I think I am closing my time. So I will just close with this particular thing. So the results, you can see different phase waveforms and then the phase neutral current. And this is the histograms, the probabilities it will show. You can see that there is actually this is a fault in phase A. And you can see that only in phase A, there is some measure appears, whereas others, it doesn't show much. Again, it shows in the neutral because neutral has some current during the fault. Similarly here, this is a three-phase fault. This is capacitor's transformer energization. I'm sorry about that. Yeah, okay. So in the transformer energization, so basically there are different, maybe I think I have mixed some things. Yeah, so basically you can see that there are some anomaly you cannot clearly see from here, but one of the phases has a decaying DC component and some harmonic content, and the remaining phase is not much. So you can see the anomaly here. This one is a capacitor switched at around 2 seconds, or sorry, you can see that around 0.5 seconds somewhere it got switched. So that time you will see the anomaly. This is a real-time thing that it will show on your dashboard if you do it real time. Okay, so this is another with the comparison with existing methodologies when we did. So basically that methodology actually shows continuously some measure, whereas with our approach, wherever there is a switching, you will see that there are two measures that are appearing. So it is very sensitive for events in the system. But of course, you should have a reference diagram for which you are, with respect to which you are actually comparing. So these are something which can be used in anomaly detection. So this is, I'm not going into the details, but showing you the results. Some anomaly in this software, in this waveform, you can see that it is detected very clearly. Okay, so that's all I have from my side. Any questions?
Participants, if you want to ask any questions, please.
See, I see about 38 participants and not even a single question makes me boring actually. If this is what happens, then there is no point in actually giving any lectures, frankly. You are all faculty members. I know you are all faculty members. And if you don't ask questions, how do you expect your students to ask questions?
Sir, exactly right, sir.
Please ask questions. Any questions, please? Can you all unmute yourself and talk to me, please? Okay, if not, I have to ask name by name.
Hello. Hello.
Yeah, speaking.
Hello.
Yes.
Good evening, sir. Myself, G. Anil Kumar.
Okay.
Sir, you are a wonderful lecture, sir, by power quality analysis. Yesterday also I attended, sir. I am one of the faculty of Bapatla Engineering College.
Okay.
Nice session, sir. Easily, clearly understandable. That's why I am not asking any questions, sir.
Huh?
Clearly understanding, sir. That's why I am not asking any question.
No question. Okay.
Yes, thank you.
You covered so many things, sir, really. It's really, you covered so many things and so many topics. Coming to link up with even PMUs, and you link up with power qualities. Then you covered a lot of things, sir, really. It's felt very happy to have this session, really. And participants, make sure to have any questions,
Okay,
please.
then you are not asking. I will call randomly some people and I will ask.
Yeah, definitely, sir.
Hi, Anusha.
Hello, sir. Sir,
Yes.
this is Balakrishna, sir. Hello.
Yes, sir. Yeah, Balu,
Yes,
sir, please.
Krishna.
Sir, Sir, this is not regarding the PPT presentation, sir. This is
Hello,
a
sir.
general question regarding ISC, sir.
Hello,
Okay.
sir.
Yeah.
Sir,
Just
is there any
just one
research
second.
going
Somebody
on?
is asking question. Just one
Hello.
second.
Balu, 1 second, Balu.
Hello, sir. This is Preeti Kabra from Deccan College Engineering, sir, Hyderabad.
Yeah, ma'am.
Okay.
Yes, sir.
Madam,
Yes, sir.
can you just wait before Balakrishna finishes?
Okay, okay, sir. No problem.
Yeah.
Thank you,
sir.
sir.
Yes, sir.
Sir, is there any right now? Is there any research going on electrical vehicles, battery related, charging station related, in ISC Bangalore right now, sir?
Yes, we do work on it. So there are faculty who work on fast chargers development. I myself work on developing two-wheeler, three-wheeler chargers for with the different features in it, all that stuff. I have 3 slides which I wanted to just introduce later after this session.
Okay, fine, sir. So can you give some insight exactly what IAC is doing on this, sir?
See, basically, we work on the topologies. So we work on hardware development, different kinds of arrangements so that you meet power quality things very well. For example, you need to maintain unity power factor. You need to maintain harmonic content should be less than something. Okay. So these are the things that we will be looking at. So there are some people in the department who works on batteries and all, but we only work at the hardware that is required to charge the batteries.
Okay. I mean, converter side.
Yes, power converters.
Yeah, okay. Thanks.
Madam, you can talk now.
Yeah, sir. Thank you, sir. Sir, it was very good and informative session, sir.
Thank you.
Sir, what is the specifications you have given? It is for micro PMU, right? For distribution side.
Yeah, this is a PMU that we have developed. Yes.
So the same specification can be used, means we have to use increase the rating of course, for transmission side, sir, means for PMU.
You don't need to increase the rating for PMU. See, at the end of the day, that's why I gave you the complete details of the analog front end. It depends on the analog front end. So is it 110 volts and 5 amperes or 110 volts for PT and 5 amperes?
PT and PT, you mean
So it depends on that. That's all. You don't need to do anything.
Okay. So same thing, same process we can follow for PMU also, right?
Is a PMU. We won't say whether it is for distribution or transmission. We have to still test it for different conditions.
Okay. Generally means for distribution side, it is as the micro PMU, right?
Yeah, this is distribution system. That's why we added power quality analysis directly so that you get time-stamped power quality analysis using this with GPS time.
For this GPS receiver and this we have to take separately, or that will be there in that parallel or some hardware kit?
No. We have to buy that. So GPS receiver I have shown in the figure. It's a separately purchased device, but it has to be integrated properly.
Okay, fine. So it will not be in that board, right?
No.
Okay, sir. Thank you, sir. Thank you.
Okay, so shall I call somebody else? Anybody else?
Power quality analyzer. Sir, this is Ravi Kumar.
Yes, sir.
We have power quality analyzer, sir. It is cost about 7.5 lakhs, sir. It's the oldest one. I want to know the latest version of any kind of organization.
You just ask anybody like Tektronix or anybody, they will give you power quality analysis. But what we are doing is actually something which is low cost, not for commercial purpose, but it can be used as monitoring. Then you can say, okay, something is there, some problem is there, then you can use a commercial one to actually check whether it is really a problem or not. Whatever we built guarantees that it is accurate up to 90%.
Is there in academic purpose, is there any organization supplying this?
This particular thing, we actually wanted to commercialize to our company. But before doing commercialization, a lot of things need to be done. So I'm still working towards that. Any other questions, sir?
No, sir. Beautiful presentation, sir. You have covered a lot of things, sir. That's why I'm able to digest the things. That is the main problem.
If you give 3
Thank
minutes,
you very much, sir.
I will just go through few details.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Basically, just want to introduce this startup which just started about a year ago. And we currently have two products. Basically, I would say smart switch, which we have built, and then smart chargers for two-wheelers and three-wheelers, and the transformer monitoring unit. What we have talking about is the is not the commercial version, but we are actually building a commercial version of it. And we have analytics platform that we have built. So these are the four things. So we are still working towards commercialization of this particular things. And this is the charger that we have built. You can see any charger that is there today are all Chinese chargers. And if you bring them and check it out, and you will see that this kind of ripples on it, but whatever built by us is actually perfect unity power factor and all that stuff. And we also have the smart switch. This is for home as well as your automation purpose. And we are yet to commercialize this. We have built everything now. I think it will be available in a couple of months for a commercial purpose. But one thing is this can be used in an R&D platform also. We are planning to make the code available so that students can actually do a lot of things on it. And we are actually offering two faculty development programs. One is basically we are actually offering training on industrial IoT. So basically, this is an indigenous board, industrial IoT board with all industrial connectivity features made by Phytech Embedded System, who is one of the partners in our company. And we are providing a lab setup for the colleges, basically at a cost of 1 lakh plus GST. And we provide about 10 such boards and some sensors. And we provided 2 days demo and about 6 months remote support so that if you train your students to use this board, and if they face some issues, and we will be helping the students as well as the faculty in actually doing the projects. There is another one which we offer, which is a very dedicated program, which basically includes a faculty training as well as a lab setup. So what we do is about 4 weeks, we will be training the faculty on either online or the offline. Because of the situation, it is online, otherwise it will be online. So 2 weeks will be a rigorous training of theory, and 2 weeks they will be doing the practical, and we'll be supporting them. And this would be at a cost of 5 lakhs plus GST. So what we provide is a lab setup of 20 boards, these industrial boards, and then 5 sensor kits. And we provide a continuous 1 year technical support for all the faculty who is working on these projects, so that they can successfully deploy these devices at their location. So this is basically something from my experience that you buy a lot of things, but later you will see that you are unable to use it because you don't get the support. So this is something which we are trying to handhold the faculty in basically learning, and also making the students to learn. So this is basically train the trainer kind of a program we are offering. So anybody who's interested, you can contact me and we can do some customized programs for you if you want. So this is a company which is incorporated in ISC, and I'm one of the co-founder. And other co-founders, one is a PhD from ISC working in Bosch, and another one is MD of Phytech Embedded. And so that's all I have. So anything that you want to do something
where I can get this information
about
you send the brochure regarding this.
Yeah, you send me I mean, I have your email, so I can send you this, and maybe you can forward this to all your contacts.
Okay, sir. Surely, sir.
Sir, once again, sir, Balakrishna, sir.
Yeah.
A quick question, sir.
Yes.
Sir, is there any development program, faculty development program on Urja smart charger, sir, from your side?
If you want, we can provide. If you want, we can provide.
Okay.
That's what I'm
Because,
telling you. We have what is called as a customization program.
Okay.
So if you say, let's say you see nowadays what is happening is, I will tell you the reality.
Okay.
A lot of engineering colleges are actually getting money to do something really good for the students. At the end, they are actually going and getting some equipment purchased later. We don't even know how to use the equipment. And this might have happened with most of you people.
Yes, sir.
So what is the objective of this particular startup is to improve the quality of the faculty. I'm telling you, it's very, very straight here. And improve the quality of the faculty by hand-holding them in their decisions. If you want to set up, let's say, an electrical lab,
okay,
how you need to choose things, what you need. Many times you go and say, hey, he will give you, I will give you this setup, that setup, fax device setup, this setup, that setup. At the end, your students cannot use that at all.
Yes, sir.
I can guarantee that.
Yes, exactly.
Unless there is some customization done so that student can interact with it. This is what is the objective of our startup. So we build labs. We will. It's not that we have all the capability to get the equipment. What we have is the ability to ask the vendor, this is what I need and you need to provide, which you may not have the information.
Yes,
this is something we provide as a consulting service. If you want us to take the responsibility of setting up the labs, yes, we can do it, but it is on case-to-case basis.
Okay.
So this is something which we offer through Urja Links. We offer customized training programs on IoT right now, and machine learning.
Okay.
And these are hands-on programs. So because of that, we have to employ people. So that's why our costs and all are tailor-made for this kind of programs.
Okay. Okay. Thanks for information.
Yeah. Any questions or anything that you want to interact with me, you can call on my number. So I think initially I have provided, and you can interact on my email ID also. If you type Gurunath Gurala in Gmail, you will get all the information. I'm sorry, on the Google, you will get all the information.
Okay, sir.
So if there are no further questions, any further?
Sir, is there any startups? Can you suggest any startups for the students of final years or like any PG students for a good startups or entrepreneurs for like electric vehicles or IoT developments?
For joining or what?
Yeah, for entrepreneurs.
No, for what? They are for job opportunities?
I mean,
no, so
he's asking about internships, sir. Internships.
Not internships, sir, but they're going to start up any startup programs or like any build up a business like a small entrepreneurship.
Okay, so basically our entrepreneurship, SID, which is Society for Innovation and Development, actually incubate startups even from outside people.
Okay.
So if your students are interested in actually having a startup and they wanted to have, they can actually write to SID, and they can, they have to do a presentation and all that stuff, but they will only incubate. Incubation is different from getting funds. Okay. So funds, they won't provide any funding, but they will only incubate. What it allows you to, once you are incubated, then you are authorized to actually reach a lot of government fundings and all that stuff.
Okay.
If you are not incubated, then you have to rely only on private funding.
So, first of all, any of the startups, they need to getting any funds. Before that, they are going to any incubation center, right, sir?
They have to be through an incubation center.
Yes. Okay.
So even your college can actually make an incubation center by yourself.
Okay.
I think you need to, there are certain procedures to follow for that, and you need to get some clearances and all from the Ministry of Industry, something like that. And then you can actually make yourself an incubation center.
So what is the cost approximate it's around, sir? It may be incubation centers.
I'm not aware of that, sir.
Okay.
incubation centers, if you want to create, I'm not aware of that.
Okay. Yes. Yes, sir. Is there any questions from participants?
If they don't have questions, then I have to call those participants. Let's call one person again.
Yes, sir.
Mr. Sridhar Challagola. Mr. Sridhar Challagola. No, he's not even talking about it. Mr. Murali Krishna. Mr. Jagadish Komati.
Hello, good evening, sir.
Yes,
My
sir.
name is. Hello.
Yes, sir. Talk, please.
Myself is Sridhar, sir.
Okay.
Sir, which type of neural networks are used, sir?
Here we used almost different types. So in this case, we have used multi-layer perceptron. That is the very basic default. And then we have used recurrent neural networks. And we also used deep neural networks. These are the three types we have used. But the sky is the limit. There are so many varieties are available. But I'm telling you, before you go and choose the neural network that is needed, you first have to have a complete data set to be prepared. That itself is a 1-year job.
Okay. Okay. Thank you, sir. Thank you.
Thank you. Any other questions? Are there some young professors? I think some Muppuri Nagendra from Bapatla College. Do you have any questions, sir? Mr. Muppuri Nagendra? I'm sorry, I'm interacting with you. Otherwise,
She,
No, sir. No, sir.
Not he. Nagendra, she.
Yes, sir. Good afternoon.
okay. Madam, do you have any questions? Do you want to ask anything?
So actually, it's a nice session, sir. I got some idea, but I don't have any questions, sir. Thank you.
Okay. Okay. See, you all have to understand that we come to actually encourage you people. You have to understand that I am like you. Okay. I was a faculty like you in Anil Nirikonda Institute of Technology. And today, if I could do, you all can do. So that's what I wanted to actually encourage. So please start looking at how you can improve your research capabilities, staying in the same organizations. And I'm always there to help you. That's all. So if no questions, I think maybe we can close this session.
Yes, sir. Yes, sir. Thank you, sir. Thank you very much, sir. It's really, so far we conduct a lot of FTPs and lot of interactive sessions, but this is completely different apart from all the things, sir. It's really very, very informative and very, very knowledgeable session, sir. Thank you, sir.
Thank you. Thank you so much. That's my duty.
Yes, thank you, sir.
Thank you very much, sir. Thank you very much. Okay, bye. Thanks for coming.
Thank you.
Thank you, sir. Thank you, sir.